Hello students, so in this lecture we will be talking about dislocations. It is a one-dimensional uh, defect in crystals, whereas defects like point defects are zero-dimensional defects. Now we all know that when there is a plane of atoms like this, and which is subject to tensile stress, there is a bond breaking, and there is a shift of atoms. So if we take this atom as atom A, and this one atom as atom B, so after the application of stress, this might look like this. The A has moved here, so this is your A and this is your B. So these are the changes that is happening. So if we graphically plot this change in energy, so it will be something like this. So this point corresponding to A and B atom kept in this fashion, and this point corresponding to the A and the B atom in this fashion, and at the center is corresponding to the A and the B atom exactly on the top of each other. Now taking a derivative of this potential, we get the strength. So it forms something like this, and this point is corresponding to the maximum strain. Where strain is equal to or strength is equal to tau max sine 2 pi x by b. For small x, tau is equal to tau max 2 pi x by b. For x much lesser than the b. Now shear strength is equal to modulus times the strain, so that makes tau max is equal to g by 2 pi, which we can say is approximately g by 10, and so this tau max is the minimum stress required to keep for deformation to keep occurring. For deformation to keep occurring. And this is the theoretical strength. Now, taking a few examples for the case of steel, example of steel and copper. So, for the case of steel, this G by 2 pi, this value is 8 gigapascal, whereas for copper it is 4.5 gigapascal. So these are the theoretical strengths. However, the observed strengths are of very less valuable. 400 megapascal for steel and almost 70 megapascal for copper. These are the observed values. Now it shows that there has been a weakening, that there should be a reason why the observed values are much less than the theoretical values. The reason is plastic deformation. So consider plastic deformation. So we should first understand that it is a atomic step-by-step phenomenon. So we have a dislocation like this. Sorry. So it actually, if we apply the stress, so it actually forms like this. So it moves to the edge. So what is observed here is that we don't need to move the whole plane. One atomic plane only can cause the dislocation to move. Now it also shows the generation and movement of dislocation leads to plastic deformation. So there are two aspects to it. First of all, you need to generate the dislocation, and after it has been generated, you have to move the dislocation. So both things are important for this plastic deformation to take place, which actually explains the weakening of the crystals. Now, once a crystal is under stress, if we anneal it, form annealing, so this process will release the strain in the crystal. Now let me take a plot with strength versus the dislocation density. So it actually, this is the place where there is a annealing has taken place, and so whatever might have been the dislocation, due to the release of strain, the strength has been compromised. However, if you look at these places in the plot, these places are those where, due to lack of any dislocation, the strength in the crystal is very high. So we call it defect free regions. Whereas this region is the annealed region. So you can see that there is a significant decrease in stress due to annealing. However, if we further work harden or plastic deform, the strength again increases, and this process is called work hardening. That means you create sufficient amount of dislocations due to plastic deformations that there is a restriction in movement of one particular dislocation, so which causes an increase in strength in the crystal. Now, considering the density, for a strain-free crystal, the dislocation density is 10 to the power 14 per meter cube, whereas work hardened crystals have a dislocation density of 10 to the power 16 to 17 per meter cube. Now, these dislocations, there has been many models. So the most well accepted model to understand dislocation is called the Volterra model. Now, this model not only describes about dislocation, but it also describes about something called disclinations. So we have dislocations, and we also have disclinations. Now, the difference between a dislocation and disclination is dislocations are only associated with translational motion, whereas in disclination, apart from translation, there is an angular change associated with it. So, whereas in metals and alloys, mainly dislocation takes place, whereas it's very rare in metals and alloys to have anything called disclination. let us try to understand the difference between these two with the help of a diagram. Now, suppose the dislocation, if you know that dislocation is quantified in terms of a vector B, it's called the Burgess vector. So it is the extra lattice parameter that one has, or due to the extra half plane of atoms being generated. So this is your dislocation. So we denote it by this Burgess vector. Now there are three ways by which we can understand dislocation. For example, if we take suppose this contour tells you about atomic displacement. So you can see that there is a difference in the starting and the ending point. So this will corresponding to a Burgess vector B. Similarly, apart from this, it can be a case like this, where the Burgess vector is, this was in z direction, the Burgess vector here is in consider this as x, so this is in x direction, or it could have been like this. Sorry. So here the Burgess vector again is in this direction, so let's call it as y direction. So we can have three types of edge dislocations. So these are all edge dislocations. Similar to this, we can also have a screw dislocation. So there is a screw component here, so this corresponding to screw dislocations. So there is a twist that is taking place. And now talking about disclination. Which not only has a translation component but also a rotational component to it. So in case of translation, which we observed in dislocation, the important thing is that the faces of the atomic planes are parallel to each other, whereas in case of disclination, this condition doesn't hold. Okay. So there are basically three types of disclination. For example, one can be with like this. Sorry. So you can see that apart from this B, there is also a translation angular component associated with this. So there's an angle. Okay. And the faces are also not parallel to each other. Apart from that, you can have a rotation. So there is a rotation that has taken place here. Or you can have an angular opening like this. Uh, have angular opening. So this is called angular opening. So these are the three different types of disclinations possible in the material. Now, to summarize, if we make a comparison between disclination and disclination, so put here dislocations, and disclination. So what are the differences we can have? The first thing that comes to our mind is this undergoes translation. That this angle goes in angular opening. It's the first difference. Second is there is the stress relaxes after some time. I mean, the effect that dislocation has is more local. Okay, if we consider a larger area of the crystal, so the effect of dislocation slowly dies out. Whereas since we have an angular component associated with disclination, so as we move on, or as we take a larger area, so that angular component, due to that angular component, the stress distortion remains in the material. So second point is stress relaxes after some distance. Whereas in this case the structural distortion remains. And the maximum energy associated with the dislocation is in the short range, where the dislocation is localized. However, there is an increase in energy at long distance. And lastly, as already explained, disclinations are not common in metals and alloys.